Hello everyone, welcome back. Today we're going to take a look at volume flow rate, which is a little different from mass flow rate, which we did during our momentum chapter. So let's start out with taking a look at exactly what this is. And to do that, I'm going to use this pipe. Now, let's say we have a fluid in this pipe. So the fluid is going this way, and there's no air in the pipe, so the whole thing is just filled with fluid. Now, obviously, if you notice, there is a large radius for the pipe here and a smaller radius for the pipe here. Now, one thing you may see already is that the velocity of the fluid going through the thicker pipe is going to be different than the velocity when it is moving through the thinner pipe. And that is because no fluid, and we'll probably use water again just for simplicity's sake, can be lost or gained. So the water can't disappear and you can't get any water coming out of nowhere. Which means if I take a look at a certain volume of fluid, let's say which in this cylinder here, as it moves into the thinner section, I need to have the same volume of water. Because again, none of it can disappear and it can't be created out of nowhere. Now that means if this volume of water is being put into the thinner pipe, it is going to be stretched. Now, if the same volume of water is passing per second, which is what the volume flow rate is, and let's say that this much water passes per second, here you have a very small displacement, and here you have a larger displacement. So in other words, the volume of water is moving this far in 1 second here in the thick pipe, and this far in the thin pipe per second. So let's back up and discuss a few basics. For starters, volume flow rate has its own label, and that is called V dot. And again, just like when we did mass flow rate, that was M dot. Our units are going to refer to how much volume of the fluid passes over a unit of time. So our base units are going to be meters cubed per second. Now, let's discuss what I just went over mathematically. Basically put, since no water could be added or gained as it goes through, and I'll call this cross-section area 1 and this cross-sectional area 2, that means V dot 1 equals V dot 2. Now, I'll call this area 1, and I'll call this area 2. So if I take a look at any volume of water here, just like I brought up before, instead of displacement, I'll call this L1 and L2. So what I have shaded in here is the actual volume of water I am looking at. Breaking this down, volume 1 over delta T equals volume 2 over delta T. Again, the same amount of fluid must pass per second. I'm going to expand this again. Area 1 times length 1, which is volume, over delta T, equals area 2 times length 2 over delta T. Now, if you take a look at this right here, this is the length of the volume, but it also is the displacement of this area passing per second. So it's a displacement, which means the units are meters per second. And that is a velocity. So area 1 times velocity 1 equals area 2 times velocity 2. So in these sections, and again, these are constant velocities here, where the larger cross-sectional area is going to have the smaller velocity, and the smaller cross-sectional area is going to have the larger velocity. In short, going from the thicker to thinner pipe, this fluid is going to speed up. Let's do this with some actual numbers to get the point across. Let's say radius 1 is 3 meters, and radius 2 is 0.2 meters. And velocity 1 is 4. So the question is, what is the velocity in pipe 2? First, I'll take the equation I just derived, rearrange it over V2. Area for a circle is pi r squared. V1 is 4 meters a second. The smaller pipe is still a cylinder, so the area is also pi r squared with R2. And actually, right now, I could actually cancel out these two pi's, which gives me R1 squared times V1 over R2 squared. These meters squared are going to cancel, and you can probably already tell by the multiplication and division here, this number is about to get a lot bigger. And we get 900 meters per second. So if the fluid in the thicker pipe is moving at 4 meters a second, goes to the thinner pipe here, it's now moving at 900 meters a second. And that comes back to the same amount of fluid must pass through a cross-sectional area per second. So I'm going to put those equations over here, and let's take a look at another situation where this is going to come into play. Let's say you are filling a pool with a garden hose. So water comes out of here, and your goal is to fill up this pool with water. I'm going to make up some values here, and I'm going to say the hose is 1 and the pool is going to be 2, but we'll discuss how to do with that in a moment. First, radius of the hose will be 0.03 meters. Velocity of the water in the hose, I'll just use the 4 meters a second again. And we are going to give the pool some dimensions. We'll say length is 9 meters, the width is 6 meters, and the height is 2 meters. All right, length, width, height. Now the question is going to be, how much time is it going to take for this water to fill the pool if this is what is happening in the hose? Now, before I even touch my equations, there are a few things we can actually get right away. First of all, if I know the radius of the cross-section area of the hose and I know the velocity of the water going through it, then I can get the volume flow rate right away. Volume flow rate is area times velocity, which is pi r squared times v1, which is pi 0.03 meters squared times 4 meters a second, which gives me 1.13 times 10 to the negative 2 meters cubed per second. While we're here, I can also get the volume of the pool. So if the hose is 1, I'll just say the pool is 2. That's simply length with height, and that would be 108 meters cubed. So if you think about it, this is how much fluid is actually coming out of the hose per second. And since that fluid is going into the pool, all we need to do now is find out how much time does it take for this volume flow rate to hit this volume. In other words, I'm going to take this top equation right here and just rearrange it for time. To do that, I get delta T is volume. Now I care about the volume of the pool because that's what I'm filling, over the volume flow rate of the hose. This is 108 meters cubed over 1.13 times 10 to the negative second meters cubed per second. I do this, meters cubed cancels. This is 1 over seconds now, so it flips because you're dividing by a fraction, and you get 9.549 seconds. If I divide this by 60, I get 159 minutes, and if I divide it by 60 again, I get 2.65 hours. So in the end, all I did was take a look at how much volume needed to be filled, how quickly it was being filled, and just solve for how much time it would take to fill it. These types of problems are common because everyone kind of understands this pretty quickly, that the volume flow rate has to be constant as it goes through a pipe. But if you're actually filling a pool, there's a little mental jump concerning the fact that this volume flow rate, all it really is the water increasing in height as it fills the pool. In other words, the area is actually the surface of the pool, and that water line is rising. So it's still a volume of water passing through a cross-sectional area per second. The cross-sectional area is just the area of the pool surface instead of the area inside of a pipe. But the concept is the same. The amount of water leaving the hose per second is the amount of water that enters the pools per second. And all we have to do is find out how much time it took for that volume to be filled. All right, there's one more concept here that I need to discuss with you because it's going to be very important in the near future. For starters, let's mention something that we just confirmed, both conceptually and mathematically. And that is, if I have fluid moving from left to right here, then the water is slow in the thick pipe and speeds up as it goes to the thinner pipe. Now, because we have a change in velocity, and change in velocity is one of the most important concepts in the course, we need to talk about that. So we're going to take a look at this section right here. In other words, the pipe where the water actually speeds up. And to start out, we're going to take a look at a single particle. Now let's talk basics. That means from here to here, this particle has to increase in velocity. And if we have an increase in velocity, that means we have what is literally the most important term of the course, which is acceleration. And acceleration, by definition, is change in velocity over a period of time. Well, if we have an acceleration here, that means on this particle, there must be a net force. And that must be true due to second law. Acceleration is F net over mass. So I'm going to enlarge this and let's take a look. So there are particles all around the one particle we're looking at. And the particles are all pushing each other. Since we need to have a net force to the right, that means the force from the right side pushing left has to be smaller than the force on the left side pushing right. Because again, these particles are all pushing each other. and the larger force has to be to the right. Now, I'm going to take that same idea and take a look at it in terms of area. Let's take a small slice of the water from this section. So now I am talking about force over unit area, which means I'm not just talking about force, now I'm talking pressure. Since the water in this part of the pipe is getting faster, it is increasing in velocity, therefore we must have an unbalanced net force. If we're talking about that in terms of a slice of water, in other words, that force is on all of these particles in a cross-sectional area here, then we're talking about force per unit area. That means the pressure on this water to the right has to be greater than the pressure on the water to the left. Otherwise, this water would not be increasing in velocity. That means that the pressure in pipe 1 has to be larger than the pressure in pipe 2. So thick pipe, slow moving, high pressure. Thin pipe, fast moving, low pressure. We're going to discuss this in more detail in my next video, but basically put, you can't get something for nothing. If velocity increases, and spoiler, we're about to get into kinetic energy, that can't come out of thin air. What do you lose? Well, you lose pressure. So the fluid moving in the thick pipe, where the fluid is moving slowly, is under a higher pressure than the fluid moving in the thinner pipe, where the fluid is moving much more quickly. If there's an increase in velocity, we must have a net force. If you think about it per cross-sectional area, then we must have a net pressure to the right. So the pressure in the thick pipe is more than the pressure in the thin pipe. All right, next time we get into the big one, I'm going to end this one here. Have a good day. This is Mr. M, signing off.